Okay, so we'll continue with our discussion on alkenes and on this particular slide. And as we saw previously, alkenes can be synthesized from alkyl halides. So an alkyl halide can be converted into an alkene. And this is the first method of synthesizing alkenes by doing an E2 reaction. Okay, there are two ways of doing it, or there are two methods of doing it. So if we start from an alkyl halide and we will use a strong base for doing this reaction, then we get the more substituted alkene as our major product. Now, the more substituted alkene is also the more stable alkene. This is called a Zaitsev elimination. Now, if this base that we're using is a bulky base, then it gives us the less substituted alkene as our major product. Now, the less substituted alkene is also the less stable alkene, and this reaction is a Hofmann elimination. Now, apart from alkyl halides, alkenes can also be synthesized from alkyl tosylates. Okay, so alkyl tosylates, alkyl tosylates can be converted into alkenes through an E2 reaction. Alkyl tosylates are represented like this, where this OTS is the tosyl ester. Okay, the TS basically, to be very precise, I guess this TS is the tosyl group. Okay, now alkyl tosylates, they behave similar to alkyl halides, which means they are both good leaving groups. So the reactivity is very similar. And alkyl tosylates are synthesized from alcohols. So a tosylate like this can be synthesized from the corresponding alcohol by reacting it with tosyl chloride and a base, for example, pyridine. Okay, by reacting it with pyridine. Now the bases that are used are usually organic bases, like pyridine. So we won't use something like sodium hydroxide for doing this reaction. Now, tosyl chloride is this molecule here. Okay, so it is para-toluene sulfonyl chloride. That's what tosyl chloride is. So when an alcohol reacts with tosyl chloride in presence of a base like pyridine, then you make the tosylate. And then the tosylates can then undergo E2 reaction. So again, with starting from a tosylate, you could react it with a strong base to get the more substituted alkene as the major product. Or you could react it with a bulky base, and this will give you the less substituted alkene as the major product. So the reactivity is very similar to alkyl halides. Okay, so that's a second method. And then the third method of synthesizing alkenes is from alcohols directly. So an alcohol can be directly converted into an alkene using a dehydration reaction. So for example, we have this alcohol cyclohexanol, then you can dehydrate it using the reagent which is concentrated sulfuric acid, and you have to heat this. So when you dehydrate it, you get an alkene. Now, very similar to an E1 reaction or E2 reaction, elimination reaction, or an E1 reaction, the double bond is formed between the alpha and the beta carbons. So this is an alpha carbon, this is a beta carbon. So the double bond could have formed on the other side also, and it would give us the same molecule. So concentrated sulfuric acid with heat is the reagent that you use for doing a dehydration reaction. So these are, I would say, like the most common methods that are covered in a first semester organic chemistry curriculum that give you alkenes as the product. Okay, so we're trying to synthesize alkenes from a different molecule in all of these cases. In the next slide, we're going to look at reactions of alkenes. Now that we've talked about the synthesis of alkenes, let's continue on and discuss the reactions of alkenes. The reactions of alkenes in general are called electrophilic addition reactions. Okay, so these are electrophilic addition reactions. And there are several of these, and each one gives us a unique product. So we're going to sort of categorize them by what can we achieve by each one of these reactions or each one of these sets of reactions in some of these cases. The first one is going to be converting an alkene into an alkyl halide. So notice how this is the reverse of what we did with alkyl halides. We converted alkyl halides into alkenes using elimination reactions. Okay. This specific reaction is called a hydrohalogenation. Now, we will use a model compound like an example, an alkene, a specific example, a specific alkene as an example for going through these reactions. And the molecule that I'm choosing here is a methyl cyclopentene. Okay, now, so for doing a hydrohalogenation, what you do is you react the methyl cyclopentene with an HX. Okay, where X is chlorine, bromine, or it could be iodine. Again, fluorine is not included here because we will not be discussing fluorocompounds. Now, when we do this, react an alkene with an HX, you get an alkyl halide. In this particular case, we will get the halogen at the more substituted carbon. Notice how for the alkene that we started with, the two carbons that were part of the double bond, there was one carbon which is more substituted and other carbon which is less substituted. So when we make this particular product through a hydrohalogenation reaction, the halogen halogen ends up on the more substituted carbon. So we say we've made the more substituted alkyl halide by doing this reaction. This reaction is called Markov. It's called Markovnikov addition. Now, if we did the same reaction, okay, where instead of using the HX, we use HX, but the reaction applies to only HBr. Okay, so one of the HXs that is possible. If we use HBr but use peroxide in this reaction, then we will get the alkene or the alkyl halide, where the Br is now connected to the less substituted carbon. Okay, so we can make the less substituted alkyl bromide this way. So again, note how you can only make the alkyl bromide this way. Okay, so here the halogen is ends up on the less substituted carbon. This reaction is called an anti-Markovnikov addition. It's also called a peroxide effect in hydrohalogenation, because we're still doing a hydrohalogenation. We are adding HX, but we are able to add it in a different order, or like go from the more substituted alkyl halide to the less substituted alkyl halide. Okay, so essentially alkenes can be converted into alkyl halides through a hydrohalogenation reaction, and you can choose whether you want the more substituted alkyl halide as the product or the less substituted alkyl bromide as the product by the choice of the reagent. Okay, that's the first reaction, or the first set of reactions of alkyl halides. The second step set that we're talking about is the conversion of alkenes into alcohols. Okay, now there are three reactions that can convert alkenes into alcohols, and we'll use the same alkene as an example here to showcase what products are formed. The first reaction is using dilute sulfuric acid. Okay, this is the equivalent of adding acid into the alkene, or hydronium ions. You can view this as that. Okay, so when you do this, you get an alcohol as your final product. Notice how we get the more substituted alcohol as our product. This reaction is called the this is a hydration reaction. I meant to say this is the opposite of a dehydration reaction. So this is a hydration reaction. We are adding water to the alkene. Okay, that's the hydration reaction. It gives us the more substituted alcohol. Now, something to remember or keep in mind about this reaction is that carbocation intermediate is involved, okay, which gives us rearrangements when possible. So rearrangements are possible in this reaction. A second method of converting an alkene into the more substituted alcohol, okay, the same product, what we got from a hydration reaction. Okay, so again we get the more substituted alcohol as our product, is an oxymercuration demercuration. And what we do here is we react with mercuric acetate using water as a solvent. That's the first step. And in the second step, we reduce with sodium borohydride. So when you do this reaction in 2 steps, you get the same alcohol as your product. So it is the more substituted alcohol. Now, we can also convert that alkene into the less substituted alcohol product. That means the alcohol, the hydroxyl group ends up on the less substituted carbon, and the hydrogen goes to the more substituted carbon by doing a hydroboration oxidation. Okay, so this is a hydroboration oxidation reaction, and it gives us the less substituted alcohol as a product. So what we're seeing here is starting from the alkene, right? We can go to the more substituted alcohol, or we can go to the less substituted alcohol, again by choice of the reagent. Okay, the next set of reactions here are converting an alkene to an alkyl dihalide. Okay, converting an alkane into an alkyl dihalide. This is a halogenation reaction. So if we start with the alkene that we have, when we do a halogenation reaction, you react it with a halogen, and let's just use X2 here, so it's any halogen, and you use a non-coordinating solvent, and this would give you an alkyl dihalide. Now when the stereochemistry matters, this alkyl dihalide is obtained as an anti-product. So we get an alkyl dihalide, and this is the halogenation reaction, anti-addition occurs here. which means that the two bromines are anti to each other, and that is depicted by putting one bromine on the wedge and the other bromine on a dash bond. Okay, so you can convert an alkene into an alkyl dihalide. Now, this is an important reaction which will take us into alkynes. So note this reaction, because this reaction serves as a connection between alkenes and alkynes. Okay, and now another important reaction that you can do on alkenes, okay, is the halohydrin. So alkene can be converted into a halohydrin. So again, starting with that same alkene, if you react the alkene with X2, but now in a coordinating solvent. So chloroform here, this was an example of a non-coordinating solvent. If you do the same reaction in presence of, let's say, water or maybe methanol. Now methanol is an example of an alcohol. These are all examples of coordinating solvents. Okay, and that's because these can actually bind to like your intermediates in the mechanism. So what happens here is when you do this, and let's say if we use water as an example, when the reaction happens, you get halogen on one of the carbons, and it is the less substituted carbon that gets the halogen. On the more substituted carbon, you will get a hydroxyl group. Okay. Now, if you use an alcohol as a solvent, then your product is going to be similar, except that instead of the hydroxyl group, you will have an ether connected to it. The halogen still goes on the less substituted carbon. On the more substituted carbon, you will have an ether instead of the OH. Okay, so if it were methanol, this R is going to be a methyl group. This R will be methyl for methanol if the reaction were done using methanol. So that's the halohydrin reaction. Again, notice, so the reaction itself is called a halohydrin reaction. And what you have to notice is that the hydroxyl group or the OR group and the X are anti to each other. So it's an anti-addition here.